So I'd like to thank Hal and Jim for letting me present here. Back in Estes Park in 2016, I presented a paper called An Engineering Model of Quantum Gravity. And I've been giving that a lot of thought since. And these are some of my ideas on how we can advance this to an experimental stage. I am an engineer, not a physicist. My background is in power electronics. Primarily for the last 12 years or so, I've been doing solar power, but I'm an expert in transformers, high frequency magnetics designs, power supplies, things like that. And so my thoughts on this come from how can I engineer something that can either affect gravity or mimic gravity? And that's what I'm going to present here. So Lance did his presentation yesterday where he was referring to a scalar field. And Nathan did her presentation this morning referring to the Meissner effect and gauge potentials, electromagnetic gauge potentials. And I'm going to take it from where I left off in 2016, which is that we have the electromagnetic gauge potential can be modified by the gradient of a scalar field. And in this case, I'm promoting that gauge scalar field to a real scalar field, but the effects are the same, the math is the same. The scalar magnetic flux is the units, Webers or volt-seconds, however you want to think of it, of the magnetic field that is this scalar field. So the magnetic flux is quantized, and quantization is Planck's constant over 2 times the electric charge, the fundamental electric charge. And if you divide by another electric charge, you get ohms. So it acts as resistance. And the scalar flux is the sum of all the flux quanta. And this gives you this value that we take the gradient and we get a modified electromagnetic vector potential. And this doesn't change the electromagnetic field E and B. For example, B is still the curl of A and the curl of a gradient is 0, so it has no effect on that. You can see here, this is a type II superconductor. And as you increase the magnetic flux, what penetrates are the flux tubes. And the flux tubes can be ordered or disordered, but you can see they're quantized into individual flux tubes. And this is a nice illustration that I found. So in a 0-point field, there's a spectral energy density, which is made up of electromagnetic 0-point field in particular is made up of photons. And that's really all I'm talking about here. But all fields have a 0-point field. But for simplicity, I'm just going to refer to the electromagnetic 0-point field. And so the flux is basically twice the surface integral of the magnetic flux density. Now, I put brackets, absolute value brackets around, or magnitude brackets, I should say, around the magnetic flux density, because in this case, it doesn't need to have a direction. It's scalar. So unlike a vector field, it's a scalar field. The when you integrate over the cross-sectional area of an electron, I use the Compton wavelength squared. And the reason for this is that in the Dirac equation, which is way too complicated to put here, we have equations of motion of an electron. And those equations of motion show that the electron is like a point-like particle that has a jittering motion called Zitterbewegung. And the jittering motion basically spreads out the electron's probability cloud on the order of a Compton wavelength. And I look at gravity as its effects are length contraction and time dilation. If we can replicate these two things, we can replicate gravity. And so I look at it as, okay, if this point-like electron is being bombarded by photons from all directions, then in order to inflate it to a probability cloud of the Compton wavelength, do the calculation here with the power, and we get about 5 megawatts of power is required to inflate this cloud, point-like particle, to be a cloud the size of a Compton wavelength. Now, there's a magnetic resonance that happens. You have a gyromagnetic ratio, and that is dependent on the particle. In this case, an electron's gyromagnetic ratio is 2.8 times 10 to the 10 hertz per Tesla. So from this, you get the frequency, which is the Compton frequency. And this equates to a magnetic field of 4.4 billion Tesla. But in a 0-point field, the statistical average is 0. So the statistical average being 0 gives you a vacuum-like field. But if you measure the average magnetic field, you get 0. But the instantaneous field acting on the electron itself is 4.4 billion Tesla. And this equates to about 25 flux lines passing through the diameter of the electron. And this interpretation of the Dirac equation is kind of key to how matter can expand and contract in a gravitational field. So the gravitational field hypothesis is that it's proposed that gravitational fields may be interpreted as a reduction in the relative available driving power of the electromagnetic 0-point field. Gravitational time dilation and length contraction may then be interpreted as a loss of power from this interaction between matter and the 0-point field. It's hypothesized here that the loss of power is due to increased radiative damping within matter due to Larmor radiation. The relative radiative damping factor affects the relative ground state energy of the quantum mechanical harmonic oscillators in matter, such that the mean square fluctuations of matter reproduce the behavior attributed to and resulting from the space-time metric of general relativity. From this principle, the phenomena observed by a distant observer that are due to gravity may be reproduced by a variable relative damping factor acting on the harmonic oscillator. And this is what I presented in 2016. From utilizing magnetic resonance imaging apparatus to stimulate Larmor radiation, experiments may be conducted which may demonstrate gravity and anti-gravity accelerations. So there's a known interpretation of gravity that is known as the polarizable vacuum model. And it was originally presented by Hal Puthoff. So in there, just quickly, you take the metric and solve for the coordinate speed of light, and you get a refractive index, which is basically the square root of the ratio of the metric potentials, metric coefficients. And given this refractive index interpretation, these are your typical effects that are produced. So when k is greater than 1, the speed of light is slowed down, rulers contract, clocks run slower, velocity is slower, etc. And if k is less than 1, then the speed of light is faster, rulers expand, clocks run faster, and velocities are faster. And so from this, I found that if I interpret it as a radiative damping interpretation, then the radiative damping factor, zeta squared, 1 minus zeta squared is the inverse of the refractive index. And from this, the mean square position fluctuation illustrates how when damping is increased, lengths contract and velocities slow down, accelerations decrease, mass increases and power decreases. And it's important to note that in these equations that the coordinate speed of light and the power are covariant with the damping factor. So both vary in the same way as the damping factor. And so whatever relationships between length and time and velocity are identical using a damping factor instead of a refractive index. And remember, I said that magnetic flux is divided by an electric charge is resistance in ohms. So it reduces the it increases the resistance, and that dampens the oscillations. In this model, that probability cloud we saw on a couple slides ago, the radiated power from Lamore radiation and the power absorbed from the 0-point field are in balance. It's an equilibrium. So it's an exchange to the particle and from the particle that keep it at its scale. And when this equilibrium symmetry is broken, the particle will drift in one direction or the other. So now, gravity as a power loss. So near the surface of the Earth, we have the gravitational potential from the Schwarzschild metric, and this makes up our damping factor. And again, here's the power. So omega naught is the natural frequency of a harmonic oscillator, could be in an atom or whatever, and that frequency will be damped by the damping factor. And so again, I said that, for an electron to be inflated to its normal size requires about 5 megawatts. And when that electron is in free fall, geodesic motion, it's in free fall, then it's losing power and contracting as it falls toward the Earth. As it loses power, it's losing about 8.8 times 10 to the minus 29 watts per second out of that 5 megawatts. So that's for each electron in matter, that's how much power it's losing. For a proton, it's a higher mass, but we end up with a slower value, and it's 10 to the minus 25 watts per second. And in general, just G is, of course, G is the terrestrial gravitational acceleration, 9.8 meters per second squared. If you square that, you find out that matter as it falls loses about 100 watts per second per kilogram, which that's the good news, because really it's not a large number. If you think about it, it's only 100 watts per kilogram per second is what matter is losing as it falls toward the Earth. And so using a simple harmonic oscillator in a gravitational field, we define the gravitational potential in the same Newtonian way. And we take the gradient of the potential, we get G at 9.82 meters per second squared. And using the gyromagnetic ratio of an electron, the primary hypothesis is that the energy, being h f naught, your Compton frequency, is related to this magnetic field, which we said was about 4.4 billion Tesla. And so what you have is a gradient in this field that exerts a force. Now, geodesic motion has no forces. Everybody knows that. But there is several things going on here. As a particle falls along a geodesic, the Ricci scalar represents how its volume changes along that path. So it is actually contracting in volume. And if every subatomic particle, every fermion in matter is undergoing the same force, then there's no way to tell there's a force being exerted, and your geodesic equation comes out the way it should in general relativity. So, so the particle loses energy as the scalar magnetic flux density decreases. And that's how it's losing its power as it falls. So testing the hypothesis, we have the acceleration, which is the gradient in the square of the scalar, the damping factor. And we can back calculate this to be the ratio of the scalar magnetic flux density relative to the initial value. And then use this to calculate that this would give us G. And the refractive index, as we defined before, 1 over 1 minus the damping factor, is just the ratio of the fields. And going back to the gauge equation, the scalar field, which is just the flux without the vector, without the magnitude, just the flux itself, is a ratio of the initial flux in a vacuum versus the reduced amount of flux near matter, like the Earth. So the Earth essentially is filtering out some of that field. It's absorbing it, or it's reducing the number of harmonics, reducing the flux. And in a sense, that is what changes this background scalar field in the presence of the Earth to generate a gravitational-like field. Controlling magnetic resonance and gravity, applying a uniform magnetic field to control the Larmor oscillation frequency of an electron also aligns the electrons either parallel or anti-parallel to the spin. The anti-parallel state has a slightly higher energy. The parallel state has a slightly lower energy, but the lowest energy state is when everything is random. So, like we said, the statistical average in a vacuum is that this magnetic flux density is 0, but it's because the flux is random. The direction of the flux is random, but the photons that are interacting with the point-like particle are hitting it randomly from all directions, but the instantaneous field of those collisions is about 4.4 billion Tesla. So it all averages out to 0, but at that scale of an electron, it's not 0, it's very strong. And that is where the magnetic resonance imaging comes in to do experiments. So if this slide, it's kind of maybe a bit of a stretch. You guys who know GR and the math better than I do can probably do a better job than I can on this. But I found a paper that I interpreted a little bit differently. But if you assume that the vacuum is a uniform value spectral energy density across a, uniformly spread out in the vacuum away from matter, and then it's losing flux and losing energy due to damping effects, these flux are subtracted from it. And this is interpreted like poking holes in a surface. And using the Gauss-Bonnet theorem, the Gaussian curvature, kappa, is dependent on the number of holes in the surface. And using the Planck area, as did Bekenstein and Hawking, the total area of the holes is determined. And in the equation over here, alpha is just an arbitrary constant. It's not the fine structure constant or anything. But the number of holes is equal to the energy density multiplied by the 4 volume over the minimum uncertainty. And from this, the Gaussian curvature provides the 3-dimensional scalar curvature, which represents the contracted Einstein tensor. And simplifying from this idea, you can recover Einstein's equations. So if the spectral energy density is like uniform and you're subtracting flux from it, then it's like poking holes in the field. And those holes get poked in it, causes curvature. And it's kind of a stretch, but that's the idea behind this, where you can recover Einstein's equations. Now, I took and looked at electron magnetic resonance And this is where the experimental comes in. And this is what I would like to do with experiments, but I have not done it yet. I did buy some materials to put together an experiment, but I need a Faraday cage and I need some more equipment to be able to actually physically measure something. So if you apply a uniform magnetic field, not a random field, like in an MRI machine, you can stimulate Lamor oscillations. And this is how an MRI machine works, is it stimulates these oscillations, and the frequencies are different depending on what type of tissue that field is penetrating. And the frequencies that get sent out from the body then are captured and filtered to produce an image on the computer. And, so here, using that same kind of technique, we know that it can penetrate the body, it can penetrate other materials. And so how well can we make the field penetrate into all materials depends on its frequency, which really has to be extremely high, like an electron Compton frequency, and it would penetrate into the material and stimulate Lamor oscillation. So here I did a rough back of the envelope calculation using the mass of an electron and its gyromagnetic ratio, and calculating the frequency, then calculating what the force would be, and find that an electron in free fall has to have a gradient in the magnetic flux density of 4.8 times 10 to the minus 7 Tesla per meter, which equates to a time dilation or a frequency decrease as it falls of 13.5 kilohertz per meter. Again, it's not a very big number. 13.5 kilohertz is not a large number, but it's a shift in like the Compton frequency, which is a very large number. And then I did the same calculation for a quark, up quark, which is about 60 kilohertz per meter. And a down quark is 124 kilohertz per meter. And protons about 24 and 24 megahertz per meter, and the neutrons about the same. So these are the shifts in the frequency that occur as a particle falls towards the gravity well. So, when the spin state of the Dirac particles are entangled, like two electrons are entangled with each other, they share a common bundle of magnetic flux from one to the other. This is part of the entanglement. In a vacuum far from other material objects, this bundle is highly coherent. So the frequencies of the two particles are coherent with each other. They're coordinated. They're phase locked. And we represent that here as B naught, which is the initial flux. In the presence of other objects, such as planets, etc., the entanglement loses coherence and the value of B naught is reduced. So it causes interference, destructive interference, damping that reduces that value, and the oscillation slows down. The probability cloud contracts, and this gives us length contraction and time dilation. And so natural gravity is when Dirac particles that are processing about a random magnetic flux axis lose frequency and energy as the entangled flux loses coherence. This results in something very similar to gravity, and hopefully something we can mimic in a laboratory. That's the goal. So artificial gravity, utilizing our understanding of nuclear magnetic resonance and electron paramagnetic resonance, we can stimulate identical effects in matter. What is required is a suitable bandwidth to assure maximum coupling between the RF field and the material object it is applied to, and a suitably sized scalar magnetic field gradient to guide the precessing particles in the desired direction. So you can imagine a ship, and we have this magnetic field generator, and the magnetic field generator penetrates all the atoms in the ship, and then we shift the field so that the precession and the frequencies drop if it moves in one direction. And that is how you would induce a free fall on the ship, like a warp drive. Now, where does this background field come from in the first place? You know, I think, like Jim, it's a Mach effect. It's the background field, the 0-point field, is really all the other fields in the universe that are applied to this point here that we're measuring. So, and then matter nearby affects that field. So anti-gravity, on the other hand, is a little different. And it's more than just directing the field gradient away from the Earth. In a real anti-gravity field, the power which drives these point-like charges, like an electron, to inflate to a probability cloud the size of a quantum wavelength, needs to be amplified to overinflate the particles, to make them expand, make your ruler stretch, make your clock run faster. That's anti-gravity. So in doing so, like an electron, all matter will stretch and inflate. Instead of length contraction, we have length expansion. Instead of time dilation, we have time accelerating and frequencies increasing. Matter becomes less dense. The energy density of the matter is decreased, as if exotic matter, negative energy density, has been added to it. So you follow me? If the volume increases faster than the energy being put in, then the density goes down, which is the same as adding a negative energy density to it. So this is the nature of exotic matter in this instance. And there's even a potential for buoyancy if the power loss gradient due to gravity can be neutralized or reversed. Somehow I lost my chat here. I don't know where it went. So, I'm not able to see the chat right now. So, here's some investigations that I'd like to do, or I'd like to see somebody do, or work with somebody to do them. Would be given an RF source, what percentage of a sample material can be made to resonate, and at what applied field strength? And then what are the governing equations determining the maximum weight loss and gain possible on like a crew or cargo of a real mission? And how can the weight loss be best utilized on a mission to like the ISS or a long duration flight? And are there side effects that would hurt humans, of this technology? Testing various materials across a broad spectrum of RF inputs to determine the feasibility and determine the best approach to maximize the weight loss of all materials. Can we generate enough acceleration to obtain measurable weight loss of a material test sample, which I think tomorrow we may hear someone who did that experiment using electron paramagnetic resonance that actually was successful? We'll see. Can we generate enough acceleration to overcome the entire weight of a test sample to provide propulsion? Like I like to say, stick it to the ceiling, so to speak. And then there's some conjecture. I mean, can the acceleration effect be broadcast out into space to provide like a defensive shield? Or can the acceleration effect be used to provide inertial stability to an aircraft or a spacecraft, like inertial dampers? Or can the acceleration effect be used to provide propulsion, and what speeds are realistically attainable? So this is the crux of the model, the engineering model of quantum gravity. And I'd like to thank Kelvin because back in 2015, I wrote a paper called the Electromagnetic Quantum Vacuum Warp Drive, which he was kind enough to publish in JBiz. And then also the paper on an engineering model of quantum gravity was published.
Yeah, how'd you not hear the whole phone?
2016 Estes Park workshop. So, so that's really,
That is not what that.
I'd like to just briefly go over some things I tried in the last few years. Behind my head here, you see my my Mega Drive. I built this using 50 millimeter PZT discs, Steiners and Martin, and I was able to replicate the waveforms, which you see on the oscilloscope there, and got that Boss amplifier on Amazon for like 60 bucks. It's like 400 watts and dual channel, and I have a dual channel frequency source. So this Mega Drive resonated at about 22 kilohertz, and I was able to build two of them and make them resonate, but I don't have a thrust balance, and I was unable to build one. After seeing Paul's and Shelley's method of using springs, I think I might try that now and see if I can get some motion out of it. Anyway, I'd like to open it up for questions now. Thank you.
I have a question.
Go ahead, Jose.
This is Jose Rodal. As I understand it, correct me if I'm wrong, Todd, you are proposing to have entropy associated with the quantum vacuum. Is that correct?
I haven't put entropy into the equations at all.
You have a damping term in the quantum vacuum. Is that correct?
I have a damping term near matter.
Oh, only near matter.
Only near matter. Where it's far from matter, like if there was no matter, then it wouldn't have any damping. It's an equilibrium. The power input is equal to the power output. So
hold on a second. So there is a damping term inside matter. Is there, let's say that you have a boundary between the matter and the vacuum. Are you saying that the damping term is only inside the boundary, inside the matter, or there is damping as well outside the matter into the vacuum?
There is only damping where the, like say the field of the Earth, which is just a, uncountable number of atoms, is radiating random flux, which then causes destructive interference with the matter in the test object that's in free fall.
So you're proposing that in the vacuum itself, you have a damping term.
Yeah, well, there is a field that is the 0-point field plus whatever fields are radiated by the Earth.
Yes, but it's in vacuum and you have a damping term. Now, let's think about that. Many systems, for example, a perfect crystal lattice has a unique ground state and therefore has zero entropy and absolute zero. It seems to me that if you are positing to have a damping term in vacuum, you have a degenerate system, and therefore if it is degenerate, you don't have anymore a unique quantum vacuum state, but you have a degenerate system of many levels of quantum vacuum, similar to Sonny White proposes also to have a non-unique quantum vacuum. Have you thought about that? Is your theory associated with a unique state of quantum vacuum, or is the quantum vacuum that you're proposing able to have different levels of state?
It can have different levels. It's okay, dynamic.
Thank you.
So in the absence of matter, you have a pure 0-point field, which is 1/2 h bar per frequency mode throughout the entire spectrum. And then near matter that has its own fields, that matter is interacting with the 0-point field, which then subtracts from the 0-point field. It reduces the the strength of the 0-point field, and therefore the probability cloud of the electron, for example, as I showed, would then contract because it's taking away from that 5 megawatts it takes to inflate it to that size. So in a pure vacuum, far from matter, it takes 5 megawatts to inflate a point-like electron up to the size of its Compton wavelength diameter. And then when you bring it near the Earth's field causes destructive interference, which then causes that probability cloud to contract because it's losing power.
Okay, another question. Have you thought about, and I'm borrowing Nathan that brought it up in the group chat. Have you thought about the energy conditions that have been postulated in general relativity, for example, by Hawking and Ellis, the strong, weak energy conditions, and also have been postulated by Penrose, for example? It seems to me that in your theory, they are violated.
No, because it never goes negative. The energy density is always positive. It's just not equal to the same value as in a vacuum far away. So yeah, you could say that, like I said, it's like adding a negative energy density to the positive energy density, but the energy density in total is always positive.
So by the quantum vacuum, isn't it the 0-point quantum vacuum? And
Yeah.
if it is degenerate and it has many levels, isn't it negative or possibly negative?
I don't look at it that way. I mean, I look at it as it's always positive. It's just not as strong as it is in like a pure vacuum far from matter.
Thank you.
Yeah, so I could talk a little bit about the experiment I had planned.
Yeah, we'd like to hear about that too, Todd.
Absolutely.
Yeah, so one of the things I've done is I've gotten some very strong, powerful magnets that I can align to produce a relatively uniform field. David Jenkins gave me some information on how to build an MRI. I have not had a chance to put that together, but he gave me the control circuits that I'd need to do it. But part of that is you need an extremely uniform magnetic field. So I got some graphite magnets, or actually not graphite, ferrite magnets that are very strong and uniform. But the idea was, how do I couple the RF signal in a way that gives me a randomized field to induce the electrons to precess and nucleons to precess? And so what I was trying to do is use a Tesla coil to generate a high frequency RF field that could couple to the test object and then measure its weight. And so the objective being is to try to find an area in the field that's not exactly uniform, that has a bit of a gradient to it. And then in that area of the field, when the Tesla coil is broadcasting some RF, it would cause, resonance within the material, which would then affect its weight. But to do this, because some of the frequencies generated would be in the microwave range and quite dangerous, I need a Faraday cage and some other stuff that can get kind of pricey, and I have not had the funds to do anything like that yet.
Todd, what's really important for the laminar magnetic field is really the shape of the iron. And we just came back from the machine shop where we're creating iron pillars for the electromagnet. And we've had quite a bit of trouble getting the field pretty laminar, but right now it is almost perfect for, I would say like 75% of the
yeah, up to about 3/4 of the total diameter of the internal field. We have a pretty good laminarity. We just picked up on a rent-to-own a magnetic field meter, a very, very nice one made by a company that pretty much just makes that thing and two other pieces of equipment. And so we got a good profile of the electromagnet earlier. We have now 20 pounds of copper on there, which is sufficient to generate somewhere between 3,000 to 4,000 Gauss in that range, so that we can force more precession. And then we'll be transmitting in the 9 to 9.5 gigahertz range. So we've got a traveling wave tube amplifier hooked up to a high frequency waveform generator, and then we are analyzing it, because the waveform generator isn't that accurate in frequency, with a spectrum analyzer, which is accurate enough, and we're probing that at the output. And so basically we're just blasting microwaves in from the side of the sample. And now that we've got the electromagnet rebuilt with twice the copper, and we can generate a significantly steadier and stronger field, we just did that just a few hours ago, we should be set up to do that experiment.
So you're going to do a demonstration tomorrow?
Well, depends if it does something or not.
Okay. Okay, good. Yeah, Mark and Jeremiah are working on something very similar based on Alzafon's paper. And I actually came up with these ideas independent completely, because I had never really heard of Alzafon until after this was written. But I read through quite a bit of his material, but I'm not, it's not 100% clear to me, that his theory is correct, but the experiment is very similar to what I'm talking about here, which is going to be very interesting.
We liked it because it was something engineerable, and just like you, we're on the engineering side of things. We want to see the practical examples done and conducted in the lab, and we want reliable results with steady readings that are way past the noise floor range. So all of those things have been challenges up to this point, and it's taken a lot of time and a lot of effort to remove all the errors out of the system as much as we can. And so we still have a few more configurations to test, but at this point, it's starting to get to the point where when we're inputting our signal and we're seeing we hit a very specific wave band, and there's a change. Although that change is noisy, it's very much locked onto a specific frequency, and we know that the frequency is not affecting the measurement equipment that we're using at that exact point. So something else must be going on in the sample.
All right, and there's also a couple of different theories about why the experiment would work. We're not going to concentrate on that. We just want to concentrate on whether the experiment works, what kind of weight loss we can gain or lose or gain, and what orientations create the most effect. And we also have all different types of samples that we're going to try. Alzafon recommends using an ultra pure aluminum mixed with a little bit of iron, cast in epoxy. We did that exactly as he subscribed, and we also put it in a vacuum chamber to remove all the bubbles. So we have very pure samples. We have like an array of like 15 different metals that we're trying in all different combinations.
And dielectrics, various other things, some oxides.
When you're dealing with more precession of the electron, that's uniform across everything. It's 28.025 gigahertz per Tesla. So anything you stick in there should be affected somewhat. Some will be affected more than others, depending on the hyperfine coupling between the electron and the core.
Right. Yep. I bought a Gauss meter to measure the magnetic field, and I also have a thermal probe, laser thermal probe, and a scale that can measure down to micrograms and input that data into a data logger. So I have the equipment, and all that cost a pretty penny and left me penniless. So I'm still working on getting the rest of it, the Faraday cage and everything else set up. And, it's engineering by the seat of your pants kind of thing. But
we're just joking about that earlier today and yesterday. It's really what we're doing is everything on a shoestring budget.
Yeah. And that's where I'm at too, as, I started out back in the 80s as what I referred to as an improvisational engineer, taking whatever was around the company's lab and building test equipment.
Amen to that. It's exactly what you have to do if you don't have a huge budget to work with and a whole staff and team to help you.
Yeah. So, all right. Appreciate that. Thank you.
We appreciate what you're doing. Can't wait to see the results.